Hello friends, today we are going to discuss some of the questions on mole concept as a part of revision for JEE. So before going on to questions, let's discuss some of the basic concepts that you all must know at each and every moment whenever you start solving any question on this chapter. So whenever we make any solution, the identity of that solution is specified by its concentration, as we all know this. Now the question of the concentration of any solution is represented by various methods like strength, molarity, molality, normality, So, what is strength? Strength is the weight of solute divided by volume of solution. This is strength. Its unit is gram per liter. Now, if we divide this strength by the molecular weight of solute, then we will get the number of moles, and that has got another terminology known as molarity, which is number of moles of solute divided by volume of solution. Its unit is mole per liter. Okay. Now, if we deal with the mass of solute and the mass of solvent, then we get another term to represent concentration, that is known as molality. Molality is the number of moles of solute divided by mass of solvent. Remember, here we consider mass of solvent, not the mass of solution. So its unit is mole per kilogram. So by looking at the units, we can say that in case of strength, weight of solute is taken in grams and the volume of solution is taken in liter. In case of molarity, number of moles of solute is taken and the volume of solution is taken in liters. In case of molality, number of moles of solute are taken and the mass of solvent is taken in kilogram. And there is another term known as normality. Normality is number of equivalents of solute divided by volume of solution. Volume of solution. Its unit is equivalent per liter. So, if we compare the formula for molarity and normality, we come at a conclusion that normality equals molarity into n factor. As we know that number of equivalents of any compound equals molecular weight the number of equivalents of any compound equals weight of compound divided by equivalent weight. Equivalent weight. And equivalent weight we get it from the formula of molecular weight. Molecular weight divided by n factor. And n factor, as we know, it is the acidity of bases or basicity of acids, or if any compound is undergoing the redox reaction or oxidation or reduction, then the n factor is the total number of moles of electrons exchanged by 1 mole of that compound. So let's discuss now another topic known as vapor density. Vapor density or relative density. It equals density of gas divided by density of hydrogen. So the vapor density or relative density of any gas equals the density of gas divided it by density of hydrogen. On simplification, we get the formula vapor density of a gas equals half into its molecular weight. Molecular weight. Now, just take care, molecular weight is represented in gram per mole, but vapor density is dimensionless because density of gas divided by density of hydrogen. Since this is a relative density, therefore this is dimensionless. Hence, we do not use any unit here. Don't write it is half of molecular weight and the unit as gram per mole. It is not so. In magnitude only, this is half of molecular weight. Okay. Now, gram molecular weight of a gas is gram molecular weight of a gas equals weight of 22.4 liter of gas at STP, that is standard temperature and pressure. Hence we can say that therefore 1 mole of a gas occupies 22.4 liter volume at STP. So now let's discuss another term known as limiting reagent. Limiting reagent. By definition, limiting reagent is the one, it is the species which gets consumed completely in a chemical reaction. Suppose there is a reaction A plus B giving us C. So initially if we take 1 mole of A, 0.5 mole of B, and initially since there is no mole of C, but after the reaction there will be 0.5 mole of A still left in the vessel, whereas B will be completely consumed and C will only be 0.5 mole in the vessel. So we are still left with the reagent A, but the reagent B has been completely consumed. Hence, this is the limiting reagent in this reaction. Okay. Now, remember that if in case of any dilution, number of moles remains constant. Okay, suppose we have got 100 ml of 1 molar solution of NaOH and we want to dilute it to 0.5 molar, then the initial number of moles of NaOH and final number of moles of NaOH are going to be same. They are going to remain constant. So we use the formula as M1V1, that is the state 1, molarity before dilution and volume before dilution equals M2V2. Okay. And in case of titration, remember the species, in case of titration, species react according to their number of equivalents. Species react according to law of equivalence. That is, suppose if any acid and base, they are reacting with each other, then at equivalence point, that is at end point, total number of equivalent of acid will be consumed by the same amount of equivalent of bases. Hence, we can say that whenever two species react, then the number of equivalents, that is N1V1 equals N2V2. Remember this formula because this is very extensively used in this chapter, especially during titration. Whole titration is based only on this formula. So there is another concept known as Dalton's law of partial pressure, although we are not going to discuss it in this chapter. Dalton's law of partial pressure. This law you will come across especially in gaseous state and equilibrium. So just we'll see what's the definition of it. It says that total pressure. It says that total pressure exerted by the mixture of non-reactive gases. Remember this, non-reactive gases. Non-reactive gases is equal to the sum of the partial pressure of individual gases. Or the partial pressure of individual gases. So we are not going to discuss this law in detail right now. We will be discussing it in gaseous state. So these are some of the concepts that you should always remember before attempting any question. So now we will move on to questions. The question 1 says that NaCl is used to prepare Na2SO4 by the reaction 2NaCl plus H2SO4 gives Na2SO4 plus 2HCl. If the reactant is 95% pure and product is only 85% pure, what weight of NaCl is used up in producing 1 kilogram of impure Na2SO4? Okay, the thing to consider in this question is that 2 moles of NaCl reacts with 1 mole of H2SO4 to give 1 mole of Na2SO4 and 2 moles of HCl. Okay, so let's approach this question. Let the weight of NaCl required equals X grams. We are asked that what weight of NaCl is used up in producing 1 kilogram of the impure Na2SO4. Okay, so let X amount of NaCl has been used up to produce impure Na2SO4. Then Therefore, mass of pure NaCl, reactant is 95% pure. It is given that reactant is 95% pure here. Therefore, since we have taken x gram of NaCl, therefore mass of pure NaCl is 95% of x. That is 95 upon 100 into x gram. So this is the mass of pure NaCl. And since the mass is this, therefore moles of pure NaCl is the total mass divided it by molecular mass of NaCl. We know that molecular mass of NaCl is 58.5 gram. Hence, total number of moles will be this much. 95x upon 100 into 58.5. Okay. Now, since 2 moles of NaCl gives us 1 mole of Na2SO4. So, whatever moles of NaCl we have used, we are going to get the half mole of that much amount as our product. And hence, moles of Na2SO4 produced is the half of this much amount. Whatever amount that we have got here, the half of this is the total number of moles of Na2SO4 produced. So, moles of Na2SO4 produced is 95x upon 100 into 58.5 into half. Now, since we have to produce 1 kilogram of impure Na2SO4, so the total weight of product should be 1 kilogram, out of which 85% is pure. Okay, since 85% is pure and the total weight should be 1 kilogram, therefore the total amount of Na2SO4 what we are getting is 85% of 1 kilogram. So, weight of product is 85% of 1 kilogram, that is 1000 gram. Okay, so this equals 850 gram. But from here, moles of Na2SO4 produced is this much. So moles of Na2SO4 is 95x upon 100 into 58.5 into 2. Therefore, weight of Na2SO4 equals, if we multiply the number of moles by molecular weight, we will get the actual amount of weight that has been produced by this reaction. So, molecular weight of Na2SO4 is 142. So, 95x into 142 divided by 100 into 58.5 into 2 is the total weight of Na2SO4 produced. We want 850 gram of this weight. Therefore, if we equated 850 gram, our problem is solved. Now, from here, we get the value of x as 850 into 100 into 58.5 into 2 divided by 95 into 142. So, this is the value of x that is required for this reaction to go on according to the given conditions. So, from here the value of x comes out to be 737.2 gram. So, this is what we wanted, and hence we can say that 737.2 gram of NaCl, of impure NaCl, gives us 1 kilogram of impure Na2SO4. So, this question has been solved. Let's go on, let's move on with another question. The question says that iO3 negative plus I negative plus H plus gives I2 plus H2O. If molecular weight of IO3 negative is M, what is the equivalent weight of IO3 negative? Okay, so in this question we are asked to find the equivalent weight of IO3 negative. So for this we know that molecular weight of IO3 is M. If molecular weight is M, we know that equivalent weight equals molecular weight by N factor. Therefore, in this question we have to find the N factor of IO3 negative. So in this case it is the difference of the oxidation number of I in IO3 in reactant and the product where it is getting formed. Therefore, oxidation state of oxidation state of I in IO3 negative is let it is X. Therefore, X minus 3 into 2 gives us minus 1. From here, X equals 5. Now, going to our product is I2. So, oxidation state of I in I2 equals 0. In this case, it is 0. Therefore, N factor is 5 minus 0 equals 5. This is our N factor. Hence, we can say that equivalent weight equals molecular weight by 5. This is our answer. This is what we have to prove. Okay, so let's move on to next question. The question says, it takes 2.56 milligram of 1 molar KOH to neutralize 0.1254 gram of H2XO4. What is the atomic weight of X? So this is a titration problem. Okay, so in this question, what we need to keep in mind is that since this is titration problem, therefore N1 V1 should be equal to N2 V2 of whatever the reagents that are participating in a reaction. So, since 2.56 milliliter of 1 molar KOH is being used, the normality of KOH is molarity into N factor. N factor is the acidity of this base. So acidity of this base is 1. And therefore N factor also equals 1. Hence normality of KOH equals 1 into 1. 1N. Since the volume we are given is it's 2.56 milliliter. So we can say that in this reaction, at equivalence point, that is at neutralization point, N of KOH into V of KOH equals N into H2XO4 into V of H2XO4. Fine. So let molecular weight or let atomic weight of X equals M. Since atomic weight of X is M, let's do this part of problem with a different color. Let atomic weight of X is M. Therefore, molecular weight of H2XO4 is M plus 66. Okay. Hence, we can say that the moles of H2XO4 used equals 0.1254 upon M plus 66. Okay, so in this case, since H2XO4, we can easily see that its N factor is 2. Therefore, number of equivalents of H2XO4 used equals the 2 times of the number of moles, and this is equals to 2 into 0.1254 divided by M plus 66. Okay, so here we know that N1V1 equals N2V2, or NKOH into VKOH equals NH2XO4 into V into H2XO4. So if we apply this formula here, we can say that 1, that is N of KOH, into 2.56 upon 1000, because volume should be in liters, equals number of equivalents of H2XO4 equals 2 into 0.1254 divided by M plus 66. So if we solve it further, we get the value of M as 32 gram per mole. Hence we can say that X is sulfur. Okay. So in this question, this type of problems, we just need to keep in mind that number of equivalents of reagent 1 should be equal to the number of equivalents of reagent 2. We just need to move to the number of equivalents. Here we have got the number of equivalents of KOH by finding its normality and multiplying it with volume. But here we have got the number of equivalents of H2XO4 by using just the simple formula of number of equivalents. Okay, so let's move on to next problem. The problem says that dissolving 120 gram of urea in 1000 gram of water gave a solution of density 1.15 gram per milliliter. The molarity of solution is, we are asked to calculate the molarity. We are given the density, we are given the mass, and we are given the amount of solute that has been used. So since we are given the density, and to calculate molarity, we want the mass of solute, which we are already given, and we want the volume of solution. So volume of solution we are not given, but we are given with the mass and we are given with the density. Therefore, from here we can calculate the volume of solution. And when we get the volume of solution, we can get to the molarity. So this is very easy question to attempt. Let's attempt this question. Total mass. We say the total mass of solution is 1000 gram of water plus 120 gram of urea equals 1000 gram of water plus 120 gram of urea. If this is 1120 grams. Okay. Now remember this thing that in case of molarity, we are bound to consider volume of solution. Volume of solution, not the volume of solute or the solvent. We just need to consider volume of solution. Whereas in case of molarity, we consider mass of only solvent. Okay. So total mass of solution is this. Therefore, total volume becomes 1120 into 10 raised to power 3 dividing by density. Density is 1.15 gram per milliliter. Okay, so from here we get the total volume as 1.120 into 10 raised to power 6 divided by 1.15. Okay. Now, to calculate molarity, I'm sorry, here this should be minus 3. So, this will get cancelled. So, the total volume is 1.120 by 1.15 in liters. This is the total volume in liters. Okay. So, therefore, molarity equals, since we know that weight upon molecular weight into volume of solution. Hence we can say that molarity equals weight we are given, it is 120 gram. Molecular weight we are given, it is 60. So molarity is 120 divided by 60 into 1.120 into 1.15. So if we solve it, we get the value of molarity as 2.05 molar. So since in this question the options were 1.78, 2.05, 2.22, special care should have been taken to calculate molarity, and which has been, because the options are very close to each other and very minor difference in our calculation or very silly mistake can lead to a different option which will be incorrect. So this question was asked in IIT JEE 2011. Very easy problem. The only concept that needed to be taken care is the total volume of solution needs to be considered while calculating molarity. Oh, sorry, here I wrote molarity. This is molarity. Okay. The objective of this question that to ask was that students confuse the volume of solution with the volume of solvent, and therefore the mass of solvent separately was given to check whether the student is clear of his or her concepts or not. So let's move on with the other question. This is a good question on titration. Nothing except for the graph is given, and we need to find out that what amount or which species is present at different positions of A, B, C or D. So the question is saying list the major species at the points A, B, C and D on the following titration curve of the titration of ammonia with HCl. Okay. Now just see this graph closely. The point A lies here. Okay. And if we see the volume of acid added at point A, no acid has been added. Okay. Since at point A, no acid has been added. Is added. At point B, as the volume of acid keep on getting added into the solution, the solution starts changing its pH. As we all know that if we add some acid into a solution, its pH will decrease. So the solution starts decreasing its pH. After reaching point B, the solution has drastically changed its pH or drastically decreased its pH, the region here. Okay. So we can say that point B is the titration point or the equivalence point. At equivalence point, the pH undergoes drastic change. So here at this point, the pH is around C, and we can say the solution has reached equivalence point. So therefore at point B, some amount of NH3 is also present. As we will keep on adding acid into NH3, NH3 will get protonated and will convert itself to NH4 positive. Okay. So at B, both NH3 and NH4 positive are present, but they are in the buffering region because we are adding acid. We have added this much of acid, but no significant change in pH has taken place. Therefore, we can say that they form a buffer type of solution. But as we have increased the volume of acid, the solution has drastically decreased its pH because the solution reached equivalence point. And at point C, we can say that this species is in significant amount than NH3. Where it is NH3. This species is in significant amount than this at point C. And here we can say that at point D also the acid is changing its pH, but it is significantly slower than this point. So let's discuss what is there at A. We can say that at point A, point B, point C, point D. of point A, as we have discussed, that NH3, only NH3 is present, therefore NH3 is present. It is yet to be acidified. Okay, at point B, both NH3 and NH4 positive are present, but in the buffering region. Therefore, NH3 and NH4 both are present, but in the buffering region. They are present in the buffering region. Okay. At point C, the titration has taken place. Therefore, we can say that NH4 positive is present at the equivalence point. At the equivalence point. Okay? All the NH3 has been protonated. Okay, but at point D, since all the NH3 has been protonated and only water molecules and NH4 positive are present, we can say that only NH4 is present along with water, which we do not consider, and more acid. Since acid is keep on getting added, more acid in solution is present. So this is what this graph is telling us. Let's move on to another question. This is a good question and it is highly recommended that please pause the video and try to solve this question yourself. This question is saying that that titration is taking place at 3 steps. In 3 reactions, titration is taking place. So let's read the question first. Question says that hydrogen peroxide solution reacts quantitatively with a solution of KMnO4 acidified with dilute H2SO4. Therefore, just keep in mind that KMnO4 is acidified with dilute H2SO4. Hence, the medium is acidic, and in case of acidic medium, N factor of KMnO4 is 5. So this is the first thing that should keep in your occur in your mind while reading the question. The same volume of KMnO4 solution is just decolorized by 10 ml of MnSO4. Okay. See, hydrogen peroxide reacts quantitatively with a solution of KMnO4 acidified with dilute H2SO4. So first titration is taking place here. After that, the second titration, the same volume of KMnO4, whatever KMnO4 we used, same volume of KMnO4 solution is just decolorized by 10 ml of MnSO4 in neutral medium. So the 10 ml of MnSO4 has decolorized the same volume of KMnO4. So another titration is taking place here. Okay, simultaneously forming a dark brown precipitate of hydrated MnO2. As soon as this is formed, it undergoes photo decomposition as well, and therefore dark brown precipitate gets formed as MnO2. The brown precipitate is dissolved in 10 ml. Here is the third titration. The brown precipitate is dissolved in 10 ml of 0.2 molar sodium oxalate under boiling conditions in the presence of dilute H2SO4. Calculate molarity of H2O2. So we need to calculate molarity of H2O2 by considering the 3 titrations that we have been given in this question. So to get ourselves more clear with this question, let's write the chemical reactions that is taking place here so that we can understand what the question is actually asking. Okay, so the question is given here. Try to attempt this question. Okay, so if we try to write the chemical reaction, H2SO4 reacts with KMnO4. So H2SO4 is reacting H2O2, hydrogen peroxide is there. So hydrogen peroxide H2O2 is reacting with KMNO4 in the presence of H2SO4. So when this reaction takes place, you must have studied in redox reaction that when this reaction takes place, K2SO4 is formed plus MnSO4 is formed plus H2O is formed, then oxygen is liberated. And if we balance this equation, we get the coefficients as like this. Since K2SO4 is given, therefore K should be 2, and here we are going to write 2. Since there are 2K, so first we balance the atoms of potassium, we write here 2. Okay, if we further balance hydrogen, we will get here as 5. We further balance hydrogen, we will get here 5, and if we balance oxygen and sulfur, we will get here 3. So if we write this complete equation, the complete equation becomes 2MnSO4 plus 8H2O plus 5O2. In the second reaction, KMnO4, same volume of KMnO4, the same volume KMnO4 reacts with MnSO4. So the second reaction will look like this: 2KMnO4 plus 3MnSO4 plus 2H2O gives 5MnO2 plus 2H2SO4 plus K2SO4. This is the second reaction, and there is another reaction taking place in this question. Another reaction is like this: MnO2 plus sodium oxalate Na2C2O4 plus 2H2SO4 giving us MnSO4 plus 2CO2 plus Na2SO4 plus 2H2O. So this is what is happening in this whole question. Okay, so let's start our discussion on how this question can be solved. Let the molarity of KMnO4, here whatever KMnO4 is used, let the molarity of KMnO4 equals M1. Therefore, moles of KMnO4 in 20 ml of solution equals 20 into M1 by, since the volume should be in liters, so we'll divide it by 1000. Okay. Now the reaction, the actual reaction that is there, the actual reaction that is taking place is MnO4 negative, here KMnO4 is in the form of MnO4 negative, going to MnO2. Okay. If we calculate the oxidation state of Mn in MnO4 negative, it comes out to be plus 7, and here it is going to plus 4 oxidation state. Therefore, N factor of KMnO4, N factor of KMnO4 equals 7 minus 4 equals 3. Okay. And now equivalence, therefore, since we know the N factor, we know the number of moles, we can say that equivalence of KMnO4 used is 20 into M1 upon 1000. This is the number of moles into N factor, that is 3. So we have got the equivalence of KMnO4 used. Now, since KMnO4 is reacting with MnSO4, okay, since KMnO4 is reacting with MnSO4 here, right? The same volume, therefore the amount is same, hence the same number of equivalents is reacting with MnSO4. Therefore, the total number of equivalents of MnSO4 should be equal to the total number of equivalents of KMnO4. Hence, we can say that, therefore, equivalence of MnSO4 equals 20 into M1 into 3 upon 1000. Okay. Now, since we know that MnSO4 n factor is 2, therefore we can say that number of moles of MnSO4 that is reacting in this reaction is the total number of equivalents divided by number of n factor. So this is equal to 20 into M1 by 1000 into 3. This is the n factor divided by n factor of MnSO4 by 2. So this is the amount of number of moles of MnSO4 that is reacting in this reaction. Okay, so the total number of moles of MnO2 produced, the total number of moles of MnO2 produced equals the total number of moles of KMnO4 plus total number of moles of MnSO4. Just see that 2 moles of KMnO4 and 2 moles of MnSO4 is and 3 moles of MnSO4 is giving us 5 moles of MnO2. Okay, the number of atoms of Mn equals to the sum of number of atoms of MnSO4 and the number of atoms of KMnO4. Okay, so we can say that if we take here x moles of KMnO4 and y moles of MnSO4, we will get x plus y moles of MnO2. Hence we can say that moles of MnO2 produced equals moles of KMnO4 plus moles of MnSO4. Okay, so we will calculate the moles of MnO2 as, therefore moles of MnO2 equals the total number of moles of KMnO4, which is here, we have got here, and the total number of moles of MnSO4, which is this, equals 20 into M1 upon 1000 plus moles of MnSO4. 20 into M1 into 3 by 1000 into 2. So this is the total number of moles of MnO2. Okay. So going further, we can into the third reaction. See the third reaction. Sodium oxalate is reacting with MnO2 to give MnSO4, CO2, Na2SO4 and 2H2O. Okay. So equivalence of Na2C2O4 reacting with MnO2. This is given to us equivalence of Na2C2O4 reacting with MnO2 equals 10 into 0.2 into 2 upon 1000. See, why this, how has it been calculated? We are given in the question that the brown precipitate is dissolved in 10 ml of 0.2 m sodium oxalate. 10 ml of 0.2 m. Therefore, 10 ml of 0.2, this gives us the molarity. This is the molarity of Na2C2O4, and since the n factor of Na2C2O4 is 2, hence the multiplying it by 2 will give us the total number of equivalents. Okay, so hence multiplying it by 2 will give us the total number of equivalents. So we have got the number of equivalents of Na2C2O4. Now the equivalent of MnO2. So from here, since the total number of equivalents of Na2C2O4 should be equal to the equivalent of MnO2, so we get the equivalent of MnO2 as 10 into 0.2 into 2 upon 1000. Okay, so this should be the equivalent of MnO2. Sorry for this. Okay, so hence we have got the moles of MnO2 reacting, the total number of equivalents of MnO2, reacting with sodium oxalate. So from here, therefore, moles of MnO2 reacting with sodium oxalate, that is Na2C2O4, will be equivalents of MnO2 dividing it by the n factor of MnO2. Since we know that the n factor is equal to, therefore if we divide the number of equivalents with the n factor, we get the value of number of moles. So this equals 10 into 0.2 into 2 upon 1000 into 2. Okay, so here we have got the moles of MnO2 in the as a function of M1, and here we have got the exact value of the moles of MnO2. If we equate both of them further, just equating them further, therefore 10 into 0.2 divided by 1000, as 2 by 2 will get cancelled, equals 20 into M1 upon 1000 plus 20 into M1 into 3 by 2 upon 1000. So if we solve it further, we will get the value of M1 as 0.04. Okay, so the equivalent of KMnO4 reacting with H2O2. Therefore, equivalent of KMnO4 reacting with H2O2 equals 20 into, okay, it equals 20 into 0.04, this is the total number of equivalents, into 5 upon 1000 equals 0.04. Okay. Since we have got the equivalents of KMnO4, therefore we can say that the molarity of H2O2 equals M2. Therefore, number of moles equals 20, since 20 ml of H2O2 is taken, into M2 upon 1000. Now if we multiply it with n factor, we will get the number of equivalents. Hence we can say that the equivalence of H2O2 used is 20 into M2 upon 1000 into 2. Okay, since we have got the equivalents, so see the equivalent of KMnO4 reacting with H2O2 is this, and since the equivalent should be same, or it will be 0.004. So since the equivalent of KMnO4 and the equivalent of H2O2 should be same, therefore 20 into M2 into 2 upon 1000 equals 0.00. 4. So from here we get the value of M2 as 0.1. Therefore, molarity of H2O2 equals 0.1 molar. So this is what we wanted to find out. So just keep in mind in this question that the 3-stage titration is taking place here. That 3-stage titration was taking place, and in case of each and every stage, the total number of equivalents of the reagents that are reacting with each other should be same. Okay, so let's see another question. The question says that 2.616 gram of an element X is reacted with an aqueous solution of NaOH and NaNO3 to yield Na2XO2 and NH3. NH3 liberated is absorbed in 100 ml of 0.11 m H2SO4. The excess acid required 48 ml of 0.25 m NaOH. Identify the element. First, we should write the chemical equation that is taking place in this whole process. The equation is taking place is X plus NaOH plus NaNO3. It is giving us Na2XO2 plus NH3 plus H2O. Okay, first that reaction has been taken place. Now NH3 liberated is absorbed in 100 ml of 0.11 m H2SO4. Now NH3 is absorbed in H2SO4. And the excess acid required 48 ml of 0.25 m NaOH. Identify the element. Okay, so the second reaction when NH3 is absorbed in H2SO4 is NH3 plus H2SO4 giving us NH4 whole twice SO4, and the excess acid, whatever acid is left, is reacted with NaOH plus H2SO4 gives us Na2SO4 plus 2H2O. So if we balance all the reactions, we will get here 4, 7, or here 4, and balancing nitrogen we will get here 2, and here balancing sodium will get here 2. Okay, so let's go on, let's move on to solve this question. Now the moles of NaOH consumed by excess H2SO4, moles of NaOH consumed by excess H2SO4. So moles of NaOH consumed by excess of H2SO4 equals 48 into 0.25 divided by 1000, because here in the question is given the excess acid required 48 ml of 0.25 m NaOH. So the moles of NaOH is consumed by excess H2SO4. Okay, so since 2 moles of NaOH are required by 1 mole of H2SO4, therefore from here moles of excess H2SO4 is the half of this value. It's the half of this value. So this is 48 into 0.25 divided by 1000 into 2. Okay. But the initial moles of H2SO4, initial moles of H2SO4, that is given as 0.11 into 100 upon 1000, because here it is given that NH3 liberated is absorbed in 100 ml of 0.11 mole H2SO4. So the molarity into volume will give us number of moles. So this equals this. And so from here we can say that the moles of H2SO4 consumed by NH3 is the difference of these terms, difference of these two terms. This is equal to 0.11 into 100 into 10 raised to the power minus 3, that is the total number of initial H2SO4, minus 24 into 10 raised to the power minus 3 into 0.25. So from here we get its value as 10 raised to the power, as 5 raised to the power 5 into 10 raised to the power minus 3. So the moles of NH3 produced, therefore moles of NH3 produced. See, the reaction is taking place in this manner. Since 2 moles of NH3 is consumed by 1 mole of H2SO4, therefore moles of NH3 produced will be double of that of H2SO4 that is consumed by NH3. So we will multiply it by 2. It is 2 into 5 into 10 raised to the power minus 3. It is 10 raised to the power minus 2 or 0.01. So the total amount of NH3 that is produced is 0.01 moles. And now since 0.01 moles is produced by NH3, so we can say that moles of NaNO3 consumed will also be 0.01, because here they are reacting in the ratio of 1:1. That is 1 mole of NaNO3 produces 1 mole of NH3, therefore x mole of NaNO3 will produce x mole of NH3. Since moles of NH3 produced is 0.01, therefore moles of NaNO3 consumed will be 0.01. Okay, so moles of NaNO3 consumed will be 0.01. Hence, therefore moles of NaNO3 consumed equals 0.01. Therefore, moles of X equals 0.01 into 4 equals 0.04. Because 4 moles of X reacts with 1 mole of NaNO3. So they are always in 4:1 proportion. So whatever amount that we are taking for NaNO3, we will have to multiply it with the factor 4 to get the required amount of X. Hence, the moles of X is 0.04. Okay. So, let atomic mass of X equals a gram per mole. Therefore, since mass of X taken is 2.616, and we know the value of the number of moles of X that is consumed, it is 0.04 here. So therefore, atomic mass of X is, since a gram per mole, 2.616 upon A equals 0.04. So if we find the value of A, we get 2.616 upon 0.04, or this implies that A equals 65.4 gram per mole. Hence we can say that X is zinc, because the atomic mass of zinc is around 65.5 gram per mole. Hence we can say that X is zinc. So here also the reaction is taking place in 3 steps. First, in case of previous problem, that is this problem. In case of this problem, we needed to go from top to bottom, that is from first reaction to the last reaction. But in this problem, we had to go from last reaction to first reaction, that is we had to move upwards. So remember that the total number of equivalents is always equal whenever two reagents react. So at any equivalence point, total number of equivalents will be same. And also, while calculating moles, keep in mind what is the stoichiometric coefficient of that particular element, because the reaction will always take place in the ratio of proportion of the number of moles. So let's discuss another question. The question says that silver, whose atomic weight is 108 gram per mole, has a density of 10.5 gram per centimeter cube. So the number of silver atoms on a surface of area 10 raised to the power minus 12 meters square can be expressed in scientific notation as y into 10 raised to the power x. The value of x is, since we know that density equals mass upon volume, let's solve this question. Since we know that density equals mass upon volume, it is given as 10.5 gram per centimeter, that is, or per centimeter cube or per milliliter. So mass of 1 centimeter cube is 10.5 gram of silver present, right? We are given in this question that silver has a density of 10.5 gram per centimeter cube, and hence 1 centimeter cube gives us 10.5 gram of silver. Okay, so the number of atoms of silver in 1 centimeter cube, therefore number of atoms of silver in 1 centimeter cube equals 10.5 into Na upon 108. Since molar mass of silver is 108 gram per mole, therefore 108 gram always contains Na, that is Avogadro number of atoms. Hence 10.5 gram will contain 10.5 into Na by 0.8 number of atoms. So the number of atoms of silver in 1 centimeter cube is this much. Or number of atoms of silver in 1 centimeter equals, if we take cube root of this quantity, then we will get the number of atoms of silver in 1 centimeter. So taking the cube root of this quantity will give us So this is the total number of silver atoms in 1 centimeter of the surface. Now, we are asked to calculate the total number of silver atoms in 10 raised to the power minus 12 meters square. So since 10 raised to the power minus 12 meters square, if we convert it to centimeter square, it gives us 10 raised to the power minus 8 centimeter square. Okay. Therefore, in 10 raised to the power minus 8 centimeter square, number of Ag atoms equals, firstly, since 1 centimeter has been squared, so we will square this term, 10.5 into Na upon 108, 2 by 3. Now we will multiply it with 10 raised to the power minus 8 into 10 raised to the power minus 8. Okay. So if we solve, we know the value of Na is 6.023 into 10 raised to the power 23. So therefore, number of atoms in question, we are given that number of atoms can be expressed as y into 10 raised to the power x. So equals y into 10 raised to the power x equals 10.5 into 6.02 into 10 raised to the power 23 divided by 108 into 10, divided by 108. Okay, and into multiplying by 10 raised to the power minus 8. So from here, y into 10 raised to the power x comes out to be 1.5 into 10 raised to the power 7. So from here we can say that y equals 1.5 and x equals 7. Therefore x equals 7, which is the answer that we wanted to come at. Okay, so from here we get the value of x as 7, and this question is solved. So this question was asked in IIT JEE 2010. So very easy questions are asked in IIT JEE. So don't be panicked to see the question. Very easy. Only mathematical concepts were involved. So that's it with this chapter. We will see. We'll meet each other in another chapter on atomic structure that we'll discuss to have a revision on. So see you there.